Hello, dear viewer. Today I would like to address a serious crisis that has occurred in chemistry departments everywhere. See, as a tutor in our university's chemistry clinic, I get questions all the time about kinetics and equilibria, and students come away so frustrated with the topic that they vow never to study it again. Dear viewer, this is a serious tragedy, because the truth is, with just a few simple rules, applied in different contexts, different situations, all of kinetics just unfolds for you. So, whether you are an aspiring enzymologist or a biologist, no shame, I hope that you too can come away with the tools that you need to survive your general chemistry class.
Let's start with the basics of what we even mean by the rate of a chemical reaction. The most basic reaction I can think of is the reaction of A goes to products. If you're following along in your chemistry classes, you might recognize the phrase elementary reaction. Nothing else is going on that would fiddle with our reaction. We can just look at this reaction right here. So what do we mean by the rate of this reaction? Really, all we mean is that for a given amount of time, some amount of A comes along and gets transformed to products. We want to know how many times that happens in a given amount of time. This is what we call the rate. You could imagine that if you had tons and tons of A's coming into this reaction, you would have P's coming out faster and faster. We represent this mathematically by saying that rate is proportional to the concentration of A. That is, to make the rate equal to A in some way, we would need a constant. And here we arrive at our rate law. We could also ask ourselves, what is the rate of the reverse reaction? What is the rate of P going to A? Similarly, if this is the elementary reaction, then we can say that rate is proportional to the concentration of P, or rate is equal to a constant times the concentration of P. Just so we don't confuse ourselves, let's call this one K1, and let's call this one K minus 1. Now let's say for this reaction that both of these things are going on at the same time. That is, A is going to P, and P is going back to A. The definition of equilibrium means that the rate of A going to P is equal to the rate of P going to A. But hey, we already figured out what those rates are. Let's just set them equal to each other, and let's see what happens. So here's an interesting relationship that we can do some algebra to. Let's see, if we just put K1 over here, divide by K negative 1. Dear viewer, does this expression look familiar to you? It turns out that the equilibrium constant K can be defined as the concentration of products over the concentration of reactants raised to their appropriate coefficients, but in this case, it's just 1. So interestingly, here's what I want to get at. This is the relationship between kinetics and equilibria, is that K is equal to K1 or K negative 1. Let's take a look at a different reaction. Let's say we have some enzyme and it reacts with its substrate to go to an enzyme and substrate all smushed together, right? Because the first step of any enzymatic reaction is the enzyme and the substrate have to get to know each other. This is also a reversible reaction, and we'll call the forward reaction 1, reverse reaction negative 1, as before. So the forward reaction, instead of being just dependent on A, is now dependent on E and S. So now we write our rate law as E and S. It is dependent on both E and S. Similarly, the reverse reaction, now notice here, we have just ES. The reverse reaction is only dependent on ES. We have an equilibrium. We can set the rates equal to each other. As before, we can rearrange things, get all the K's on one side and all the terms on the other. Again, this is products over reactants, just your normal, everyday equilibrium K. At this point, you, dear enzymologist, might be thinking, why does this look familiar? This looks familiar. You might be thinking of the dissociation constant, Kd, which is simply equal to the rate constant for ES breaking apart, divided by the rate constant of ES coming back together. Remember that all these K's, these uppercase K's, these lowercase K's, they have meaning. And this is telling you the ratio of your dissociated enzyme to your enzyme all put together. At this point, I think you're ready for a little bit more meat. Let's take a look at this reaction here. E plus S is in equilibrium with enzyme substrate all smashed together. And then this, after that, goes to your enzyme plus product. This is how enzymes work, right? They take a substrate, smush it together with themselves, and then go produce a product. Once again, label each of our different reactions. 1, negative 1. We'll call this 2. So at this point, I have a question for you. What is the rate of this overall reaction? Is it the production of ES? Well, not really, because ES isn't really what we're looking for in the end. We're looking for the change in product over change in time. We're looking at how quickly this whole thing goes to over here. So, dear viewer, what is this equal to? Remember that rates are simply proportional to the reactants that come before them. And at this point, this part right here, the reactant, is ES. It's proportional to the concentration of enzyme substrate. So our actual rate that we care about is this guy right here. And at this point, those of you from biochemistry will be shouting from the back, "This is Michaelis-Menten!" And those of you in gen-chem will be all, "What the heck are you talking about? I don't know what Michaelis-Menten is." So for this video, we won't go into that. There are many, many resources for you biochemists. Go to YouTube, look up Michaelis-Menten. But for now, I want to focus on the general chemistry applications of all of this. So to sum up, what all this tells you is that if you are given an elementary reaction, you know the rate associated with that is equal to some constant times its reactants. You also know that if you have an equilibrium, those rates have to be the same. And from here, you can do algebra to get all sorts of other things. You could get that the KEQ is equal to your products over your reactants. You get that your KEQ is equal to the ratio of the rate constants. And carrying on to more complicated reactions, I encourage you to derive a rate equation that doesn't include ES. Maybe it includes the total amount of enzyme here. The point is, it's all just algebra. Future video topics would of course include Michaelis-Menten. It would include integrating the rate law to get some more useful things. But for now, I want you to realize that it's just algebra. So take it, digest it, go off and do some enzymology.